Hey, BC Calculus, Mr. Canfield here, Chapter 23, Series Convergence Divergence Review and Classwork. Okay, so I thought it would be good to make a wrap-up video on series convergence and divergence. And yeah, so we're going to go through this table. I'm going to give you a couple pointers. First pointer is, I want to say go with your gut and check your gut. So like check your answers, and if your gut is consistently right on these, then you're gonna be able to do that on the AP exam as well. You're not gonna need to do complex testing. So additionally, add to your gut. If your gut does not already have this, 1 over n diverges, 1 over n squared converges. 1 over the square root of n diverges. These are our three comparisons that we tend to draw. So, nth term test. How does the nth term test converge? It doesn't. We don't know if the nth term test, the nth term test can't tell you convergence. Nth term test can just tell you if something definitely diverges or if it's inconclusive. So, it could converge as long as the limit goes to 0. So if the limit goes to 0 of the individual terms, then we have all these different things down here. We've got our geometric series. This formula you need to know by heart. For me, it's been pretty easy to remember. I don't know why that is relevant to you. It's one more thing to add to your formulas page, and this whole thing here has a whole lot of stuff that's really helpful. So I'm just going to jump into the examples and see what I can't figure out. So let me go ahead and pull up my work. So sorry, bear with me. I'm not going to edit this part out unless I have time later today. So just opening up my my answer guide. Okay, so if I look at this first one here, my brain goes to, well, let me see. Do the individual terms go off to 0? That's kind of my first place of checking. And no, the individual terms go off to 1. So, and I know this, and I'm going to try to do a little bit more detail than just saying I know this, I know this, I know this. So, remember when it's a polynomial over a polynomial, you can just focus on the greatest power that you see anywhere, and I see n squared, so I have 1n squared over 1n squared. As we go off to infinity, it's going off to 1 over 1, or just 1. Since the terms are going off to 1, we call that divergent. This one, 1 over n squared plus 4. Well, the plus 4 doesn't really matter, and we know 1 over n squared goes to infinity. Or 1 over n squared converges, sorry. So, and again, the reason why the plus 4 doesn't matter is if you compare a number to something squared to a continually growing number that gets squared, that constant 4 doesn't mean anything. All right. So 3, I look at 3 and I know that it converges. All right, 4, no, okay, let's explain 3. So here's how you know that 3 converges. If you didn't have this, if you didn't have the negative 1 to the n over n squared, this is going to 1 over n, right? If you look at the biggest on top, biggest on the bottom, and just kind of cancel them out, this is n over n squared. That's the same thing as thinking 1 over n. 1 over n is divergent, but an alternating series, negative 1 to the n times 1 over n, now this is convergent. Remember, all we needed if we had alternating was, does it go to 0? So if the terms are going off to 0 and it's alternating, boom, convergent. All right. Number 4. So when I look at number 4, I see that we are going to, this is kind of going to look at 2 to the n, right? 4n over 2n, the 4, so it's really just 4 over 2. That's divergent. You can also do the root test for this one. 5, So when I look at 5, I want to try the ratio test. Let me see. So ratio test says the n+1 version of it goes on top, right? Yeah, n+1 version goes on top. So n+1 version would be 1 over n+2 square root of ln of n+2 all over n+1 square root of ln of n+1. That's 1 over all that, right? So it's going to wind up flipping, and we'll get n+1 root ln n+1 over n+2 root ln n+2. And I know that like this portion of it's going to 1. This portion of it I could think about as being the square root of ln of n+1 over ln of n+2. That's infinity over infinity. Oh, I can do like I could do L'Hopital's rule on here. I see where I'm going with this. This is eventually just going to head off to 1. This, according to ratio test, this is all inconclusive. So Stu does the integral test for this. So if we look at the integral test, it's actually kind of a nice integral. If we make u equal to ln of n+1, this is 1 over n+1 is du, right? du is 1 over n+1 dn. So then when I go in and do my substitution, I wind up getting like you go through, you do your substitution, and you'll get 1 over the square root of u du. So that's a really simple antiderivative because this is the integral of u to the -1/2 du. So to do the integral of that, we'll add 1 to the exponent, get u to the 1/2, divide by our new exponent of 1/2, which is 2. We're going from 0 to infinity. Oh, wait, no, I didn't change the bounds. Oh, wait, plug in 0 for u here. ln of 0 plus 1 is 0, so that's 0, and then ln of infinity plus 1 is still infinity. So this actually does work, and we get 2 infinity to the 1/2 minus 0. So we get infinity. So the integral of this diverges, so the sum diverges, this diverges. If I was thinking about this just conceptually, I know 1 over n diverges, and I don't start converging until I hit 1 over n squared, and n times the square root of ln n, I don't think that's going to be enough to get me to n squared, up to n squared. I think it's going to be still a little bit less than n squared in terms of strength. So that would kind of be my conceptual way of thinking about it. All right, 6. 6 is a great example for us to do. Wait, no, 6 diverges, right? So before I even do the ratio test, I know 6 diverges. Why? Let's talk about it. We got n factorial over n plus 1 factorial. Like, that's close, and then the top's got an extra 3 to the n. So I'm feeling this diverges, but let me just double check. So we'll do the n plus 1 version on top. over my n plus, I'm going to do n plus 2 times n plus 1 factorial. That's what n plus 2 factorial is, right? And then it's going to be over the n version. So let me just slap the n version on upside down. Then we'll get our n plus 1 factorials cancel. Why is there another one written here? Oh, from that. Okay. And then our n factorial cancels out with the n factorial here. And then our 3 to the n plus 1. So it looks like we're left with 3n plus 1 over n plus 2. And the limit of this is 3. And remember, if it goes to more than 1, it diverges. So there we go. 7, there's another one where ratio test is good. 8's a good ratio test. I think 8's a good ratio test. He uses different tests. Oh, wait, you don't need to do ratio test on that. You can just look at that and know. Yeah, I was wrong earlier. I was saying that n has to be 2, or sorry, the exponent has to be 2. But if you remember, if we've got p series, if the power is greater than 1, it converges. So just to take it back really quick, 5 does not really make a whole lot of sense to me personally, but 5 definitely diverges. So 9, oh, I love 9. 9's fun. These are all numbers in here, right? So 2 pi is that more or less than pi plus e? Because if these were equal, it'd be 1. If the top's more, then it's more than 1. If the top's less, then it's less than 1, right? Like, so this is greater than 1 to the n, so it's divergent. 7, sine of n, remember, is an oscillation between -1 and 1. 2 to the n just sucks this down to 0, so this converges. 11, tangent of 10 over n. We know that tangent of x is nuts, just does the, almost looks like an echocardiogram or something. But this starts out at tangent of 10, and as n increases, this goes from tangent of 10 to tangent of 0, and tangent of 0 is 0. So for this one, Stu does the limit comparison for this one. I want to just, so this would be multiple choice. If they were going to do limit comparison, they would say compare this to 1 over n. So let's compare it to 1 over n and see what happens. So I don't expect you to figure out what to compare it to. I'm saying it'll tell you, it'll give you options. And the way that the comparisons will work on the AP exam, remember that limit comparison, the idea is I know that this one diverges. So if this diverges, then I need to show that tangent of 10 over n is going to be bigger than 1 over n. If I do that, then I can show that tangent of 10 over n also diverges. If tangent of 10 over n winds up being less, then it's inconclusive, because we don't know if it diverges just slower or if it doesn't diverge at all. So I know that 1 over n diverges, and if I go through and do limit comparison, so we're just trying to find the limit as n goes to infinity. we wind up getting 0 over 0, so I can do L'Hopital's rule. So that gives me negative 1 over n squared. And then that's going to be secant squared 10 over n times the derivative of the inside, which is negative 10 over n squared. So the n squareds cancel, the negatives cancel. We wind up getting 1 over 10 secant squared 10 over n as our new limit. And this time secant of 0, that's cosine, right? 1 over cosine of 0 is 1, so this goes to 1/10. And if we look at our rule here, limit comparison, as long as the limit is positive and finite, when you do this comparison like this, then it does the same thing as the original. So this one, our original is divergent, so this is divergent as well. And then our last one here, isn't 12? 12's just divergent, right? Because the top is bigger than the bottom, the limit's infinity of the individual terms. So, hope that was helpful. Bunch more practice in the back. Yeah. This is the level of depth that I need you to be able to go for the AP exam. So, obviously, there's more depth than we've done in class, but cool. See ya.